You think you know what an electron is? A little dot, dancing around the nucleus, like a planet around the sun. That's what school told you. That's what the textbooks show. Neat little circles, clean little diagrams. But here's the thing. If you follow our own physics, our best physics, strictly, logically, step by step, that little dot should have an infinite mass, not a big mass, not a heavy mass, infinite. Heavier than the Earth, heavier than the Sun, heavier than the entire galaxy. A single electron should be a black hole that swallows everything around it. But it doesn't. It's light, impossibly light. 9.1 times 10 to the negative 31 kilograms. So light you can't even imagine it. And it dances. It builds atoms. It builds molecules. It builds stars and planets and nervous systems. It builds you. So how can our best equations predict that the universe should be a catastrophe? And yet, here you are, watching this, breathing, existing. The answer is that we cheated. Yes, you heard me. We cheated. The most successful theory in the history of science, the one that predicts reality to 12 decimal places, is built on a mathematical crime. And this crime? It's the reason you exist. Let me show you how we broke math to save physics. Yes, you heard me. We cheated. The most successful scientific theory ever created, the one that predicts how light and matter interact to 12 decimal places, is built on a trick, a sleight of hand, a move so mathematically suspicious that the man who invented it called it a Dippy process. That man was Richard Feynman, and the trick? We took infinity, a number that should destroy everything, and we swept it under the rug. And here's the part that should bother you. It worked. Not kind of worked, not approximately worked. It gave us the most precise predictions in the history of science. Period. So this video is about how that happened. How three physicists, working independently, stumbled onto the same impossible solution. How they broke the rules of mathematics and accidentally saved physics. But more than that, this is about a fundamental limit of human understanding. Because infinity isn't just a number that's too big. It's a message from nature that says, when you look too close, the rules stop making sense. And there's a monster hiding in the equations. A monster that the greatest minds of the 20th century tried to kill for decades. They couldn't kill it, so they learned to live with it. Let me show you where the monster comes from. Picture a single electron, just one, floating in empty space. Now this electron has an electric field around it. You can't see it, but it's there, reaching out in every direction. Here's how I want you to think about it. Imagine you open a bottle of perfume in the middle of a room. The smell spreads outward. Close to the bottle, it's intense, overwhelming. Walk to the far corner of the room, and it's barely there. The further you go from the source, the weaker it gets. An electric field works the same way. Close to the electron, the field is strong. Far away, it fades. And the mathematical rule that describes this is beautiful in its simplicity. The strength of the field is proportional to 1 over the distance squared. 1 over r squared. Double your distance, the field drops to 1/4. Triple it, drops to 1/9. Simple. Elegant. Nothing scary here. Until you play a game with me. What happens when you get closer? Not further. Closer. To the electron, half the distance, the field is 4 times stronger, 1/10 the distance, 100 times stronger, 1,000th, 1,000,000 times stronger. Now here's the question that breaks everything. What if you go all the way? What if the distance is 0? 1 divided by 0 squared. 1 divided by 0, infinity. The electric field at the location of the electron itself is infinite, which means the energy stored in that field is infinite. And here's where Einstein walks into the room, because E equals mc squared tells us that energy is mass, infinite energy, infinite mass. A single electron, this tiny, almost weightless speck, should, according to our own mathematics, have an infinite mass. It should be heavier than the sun, heavier than the galaxy, heavier than the entire observable universe. One single electron. That's not a small problem. That's not a rounding error. That is a complete, total, catastrophic failure of our equations to describe reality. And this isn't some exotic quantum weirdness. This is classical physics. Maxwell's equations. Stuff we've known since the 1800s. The infinity was always there. We just chose not to look at it too hard. And if one electron is a catastrophe, think about the trillions of electrons in your body right now. So classical physicists had a reasonable idea. Give the electron a size. Make it a tiny sphere of charge, not a point, a ball. Sounds sensible, right? If it's not a point, you never divide by 0. The energy stays finite. Problem solved. Let me show you what I mean. Imagine a hollow copper ball, small, about the size of a marble. Now coat the inside surface with electric charge, positive charge, packed tightly together. What happens? The charges repel each other. Every positive charge pushes against every other positive charge. They're trying to fly apart. The only thing holding them together is the ball itself. And that repulsion, it stores energy. The more charge you pack into a smaller space, the more energy it takes to hold them together. Squeeze harder, more energy. Squeeze to nothing, infinite energy. So the physicists said, fine. The electron isn't a point. It's a tiny ball, like a tiny copper sphere. It has some small but real size. When the energy is large but finite, we can live with that. Clever, reasonable, and completely wrong. Because here's the trap. If the electron has a size, if it's a little ball, then it has parts. An inside, an outside, a left side and a right side. Edges. And those parts are all made of the same charge. Negative charge, repelling each other, trying to rip the electron apart. So what holds it together? We don't know. Nobody knows. There is no known force that can hold the electron together if it has a size. You'd need some mysterious glue, some new force that nobody has ever detected, and it gets worse. Physicists smashed electrons together at enormous speeds in particle accelerators. If electrons had internal structure, parts, edges, subcomponents, the collisions should reveal them. The electron should crack, should shatter, should show its insides. It doesn't. Every experiment, every collision, every test, the electron behaves like a perfect point. No structure, no size, no parts. So here's the deadlock. If the electron has a size, it falls apart. Nothing can hold it together, and experiments say it has no size anyway. If the electron has no size, it's a point. And a point means infinite energy, infinite mass. Neither option works. It's like nature is presenting us with a bill for infinite energy. And no matter which way we turn, point or ball, zero size or tiny size, we can't escape the bill. Quantum electrodynamics, QED, the most successful scientific theory ever created. And I don't say that lightly. How accurate is QED? Let me put it this way. Imagine measuring the distance from New York to Los Angeles, coast to coast, about 2,800 miles. Now imagine getting that measurement right to within the width of a single human hair. That's how precise QED is. Its predictions match experiment to 12 decimal places. 12. No other theory in any field of science comes close. So here's the paradox that should keep you up at night. How can a theory be so spectacularly right in its predictions and so catastrophically wrong in its mathematics? Because QED has the same infinity problem. Worse, actually. Much worse. See, in classical physics, the electron was a simple thing. A charged particle sitting in space, static, still, boring. But in the quantum world, nothing is still, nothing is simple, nothing just sits there. The electron in quantum mechanics isn't a rock. It's alive, dynamic, constantly fluctuating. Let me show you what I mean. Imagine a pond, perfectly still water, flat, calm. Now drop a bug on the surface. A tiny water bug sitting on the surface tension. What happens? The bug disturbs the water. Ripples spread out. Tiny waves moving away from the bug in every direction. But here's the thing. Those ripples bounce off the edges, off rocks, off other disturbances. And some of those ripples come back to the bug. The bug creates waves. The waves come back and shake the bug. The shaking creates more waves, which come back and shake the bug again. The bug is interacting with its own disturbance, feeding back on itself. An endless loop. That's what an electron does. The electromagnetic field is the pond. The electron is the bug. And the ripples? Those are photons, virtual photons. The electron emits a photon, a ripple in the electromagnetic field, and then absorbs it back, constantly, endlessly, interacting with its own field. Physicists call this self-interaction, and when you try to calculate the energy of this self-interaction, infinity. Again, the same monster. But now it's quantum. Now it's everywhere. Now it's woven into the very fabric of the most accurate theory ever created. The classical infinity was bad. The quantum infinity is worse. Because you can't just ignore it. QED is too good, too accurate, too successful. You can't throw it away. You're stuck with a perfect theory that gives you nonsense. But to understand what those physicists were up against when they gathered on that island, you need to see the full scale of this disaster. Remember the bug on the pond? The electron creating ripples and feeling them come back? That was the simple version. The reality is far stranger. The electron doesn't just emit one virtual photon. It emits them constantly, in every direction, at every energy. It's surrounded by a cloud of these ghost particles, a swarm of photons popping in and out of existence so fast that no instrument can catch them. Think of it like this. You're not just looking at a bug on a pond. You're looking at a bug sitting in the middle of a permanent hurricane of its own making. Ripples going out, coming back, spawning new ripples, which spawn more ripples. A seething, churning cloud of activity that never stops. And here's the part that matters. When you try to push the electron, when you try to accelerate it, measure its mass, you're not pushing just the particle. You're pushing the particle plus the entire cloud, the whole entourage, every ghost photon, every ripple, every fluctuation. So physicists sat down to calculate. How much energy is in this cloud? They did what physicists do. They added up every possible way the electron could emit and reabsorb a virtual photon, every possible energy, every possible direction, every possible timing, And there's the problem. There's no cap, no ceiling, no maximum energy a virtual photon can carry. The integral stretches from 0 to infinity. So when you add it all up, when you sum every ripple, every ghost, every fluctuation, infinity, again. Not a different infinity, not a smaller infinity. The same monster. The same catastrophe we thought we'd left behind in classical physics. The monster followed us into the new room. And now the situation is truly absurd. The electron, this thing we can hold in a magnetic trap, measure on a scale, weigh to extraordinary precision, 9.1 times 10 to the negative 31 kilograms. Our best theory says its mass should be infinity, plus infinity. From the classical contribution and the quantum correction. The most accurate theory in the history of science is telling us that the universe cannot exist. June 1947. Shelter Island, a small spit of land off the eastern tip of Long Island, New York. 24 physicists, that's it. No giant auditorium, no 1,000-person conference. Just 24 people in a small room, and one very big problem. Among them were some of the greatest minds of the 20th century. Robert Oppenheimer, fresh from building the atomic bomb. Hans Bethe, who had figured out how the sun burns. And a young man named Richard Feynman, who was still grieving the death of his wife and had nearly given up on physics entirely. They came because new experimental data had just arrived. Willis Lamb had measured something strange, a tiny shift in the energy levels of hydrogen that the existing theory couldn't explain. The Lamb shift. It was small, almost nothing. But it was there. And it was exactly the kind of crack that could break the infinity problem wide open, or prove that physics was fundamentally broken. Hans Bethe couldn't stop thinking about it. On the train ride home from Shelter Island, while the other passengers read newspapers and stared out the window, Bethe pulled out a pencil, and on the back of an envelope, literally the back of an envelope, he did a rough calculation. He found a way to subtract the infinities. It wasn't clean. It wasn't elegant. The math was ugly. He had to cut off the calculation at a certain point, shove in the measured value from the lab, and ignore the parts that blew up. It felt like cheating. But the number he got matched Lamb's measurement. The infinity could be tamed. Not killed, not removed, tamed, hidden. Cancelled against another infinity that nobody had thought to look for. And then the race began. 3 physicists, 3 continents, working completely independently. So each one found their own way to tame the monster. Julian Schwinger, in America, attacked the problem with brute mathematical force. Hundreds of pages of dense algebra, calculations so complex that only Schwinger himself could follow them. His lectures were legendary. He would fill blackboard after blackboard without ever looking at his notes. Shinichiro Tomonaga, in Japan, developed a beautiful mathematical framework. Working in post-war Tokyo with limited resources, limited funding, communicating by letter because the journals took months to arrive. He solved the same problem with an elegance that took everyone's breath away. And Feynman? Feynman drew pictures, simple little diagrams, lines and squiggles. While Schwinger needed hundreds of pages, Feynman needed a napkin and a pencil. He turned the most complicated calculations in physics into something you could sketch on the back of a menu. 3 languages, 3 completely different mathematical approaches. And when they compared their results, same answer. 3 translators on 3 continents, working from 3 different dictionaries, and every single one produced the exact same sentence. They shared the Nobel Prize in 1965. And the technique they all discovered? The one that cancels infinity against infinity? They called it renormalization. Feynman called it something else. He called it a Dippy process. He said it felt like sweeping the dirt under the rug. He wasn't proud of it. He was pragmatic. I don't care if it's ugly. I care if it works. Here's what they did. And please listen carefully, because this is the most absurd logical maneuver in the history of science. They said, okay, the electron has two masses. First, the bare mass. This is the mass the electron would have if you could somehow strip away all the virtual photons. Turn off the electric field, peel away the cloud, the mass of the naked electron standing alone. Nobody knows what this number is. Nobody has ever measured it. Nobody can measure it. Because you can never see a naked electron. The cloud is always there. Second, the correction mass. This is the extra mass created by all that quantum chaos, the virtual photon cloud, the self-interaction, the ripples hitting the bug. So the measured mass, the number you actually read on your scale in the lab, is the sum of both. Simple enough. Except when you calculate the correction mass, the contribution from the virtual photon cloud, the equations scream infinity. So now you have measured mass equals bare mass plus infinity. But we know the measured mass. We've measured it 1,000 times. It's 9.1 times 10 to the negative 31 kilograms. Tiny, finite, real. So what do? You do the only thing left. The thing that makes mathematicians want to throw their textbooks into the ocean. You say the bare mass must be negative infinity. You assume that deep down, underneath the cloud, the naked electron has a mass of negative infinity. And this negative infinity, when you add it to the positive infinity from the cloud, leaves behind a tiny, finite remainder. The electron we see, the electron we measure, the electron that builds your atoms. Does that sound insane? Of course it does, because it is insane. In mathematics, you cannot subtract infinity from infinity and get a specific number. Infinity minus infinity is undefined. It's nonsense. Think about it this way. If I tell you I have an infinite amount of money, and I spend an infinite amount of money, do I have $5 left? Or $1 million? Or 0? Or negative 10? You can't know. The question doesn't even make sense. But here's where physics parts ways with mathematics. Physics is pragmatic. Physics says, I don't care about the philosophy. I care about the answer. So we redefine the game. We say, I'm never going to see the bare mass anyway. I can never strip the cloud from the electron. They're inseparable. So let's stop pretending I need to know the bare mass. Instead, let's just absorb the infinity into the definition of the electron itself. Rewrite the equations so the infinity disappears. Stick in the number we measured from the experiment. And calibrate everything else from that. It's a shell game. We put the infinity under one shell, shuffle them around really fast, and then we say, look, no infinity. That is renormalization. That is the trick. That is the mathematical crime that Feynman called Dippy, and that Dirac called ugly, and that every physicist since 1947 has used every single day. Once you hide the infinity, once you perform the renormalization trick, the theory doesn't just survive, it thrives. Because now you can use it to calculate other things. Things you haven't measured yet. Things that will test whether this insane method actually means anything. One of the first things physicists calculated was the anomalous magnetic moment of the electron, a tiny correction to how an electron behaves in a magnetic field. The calculation is brutal. It took years, hundreds of pages of algebra, Feynman diagrams stacked on Feynman diagrams, thousands of terms, each one requiring its own careful renormalization. But eventually, a number came out, a prediction, written down on paper. Then the experimentalists went to work. They built enormous magnets, cooled their equipment to near absolute zero, trapped single electrons in magnetic fields for months, measured and remeasured, pushed their instruments to the absolute limits of human engineering. And when they compared the theoretical prediction to the experimental measurement, they matched. Not approximately, not roughly, not in the right ballpark. They matched to 10 decimal places. Then 11, then 12 decimal places. Let me put that in perspective. Imagine you wanted to measure the distance from the Earth to the Moon. About 384,000 kilometers, roughly 239,000 miles. And I calculated that distance with a pencil. And you measured it with your best instruments. And we compared our answers. And they agreed to within the width of a single human hair. No, better than that. They agreed to within the width of a single atom. That is what renormalization gives us. A method built on mathematical nonsense, negative infinity plus positive infinity, that produces the most precise predictions in the history of all science. Not just physics, all of science. No other theory, in any field, has ever matched experiment this closely. And Feynman knew exactly how absurd this was. He called it a Dippy process. He said it felt like cheating, like sweeping the dirt under the rug. But nature doesn't care about our feelings. Nature doesn't care if the method is elegant or ugly, clean or dirty. Nature agrees with the cheat. The answer is perfect. The method is insane, and we have no idea, truly, deeply, no idea why it works. Most people hear this story and ask, but why does it work? And that's the right question, the important question, the question that takes us beyond physics and into philosophy. Because here's something most science videos won't tell you. Most physicists don't actually believe that the bare mass of an electron is negative infinity. They don't think renormalization is the final answer. They think it's a clue, a clue about what's really going on at the smallest scales of the universe. Think about it this way. When does the infinity show up? It shows up when we calculate what happens at zero distance, when we push our equations all the way down to infinitely small scales, when we zoom in forever. What if you can't zoom in forever? What if space itself has a smallest possible size? Imagine your phone screen. From a distance, it looks smooth, continuous, a seamless image. But zoom in far enough, and you see pixels, little squares, a grid. There's a smallest unit. You can't go smaller than 1 pixel. Some physicists believe the universe works the same way. That space isn't smooth, it's granular. Pixelated. There's a smallest possible distance, the Planck length, seen about 10 to the negative 35 meters. So small that if an atom were the size of the observable universe, the Planck length would be the size of a tree. And if space has pixels, if there is a smallest distance, then you never actually reach zero. You never divide by zero. The infinity never happens. The infinity in our equations isn't a bug. It's a message. It's nature saying, you're asking a question that doesn't have an answer. You're zooming in past the resolution of reality itself. Stop. There's nothing smaller. You've hit the bottom. And renormalization, It works because it's secretly doing the right thing for the wrong reason. It's cutting off the infinity at a finite point, which is exactly what nature does. We just don't know the exact point yet. It's like trying to watch a movie through a frosted window. You can see the shapes, you can follow the plot, but the details are blurred. Renormalization gives us the plot, with stunning accuracy. But the window is still frosted. And this brings us to the deepest question of all. Imagine for a moment that renormalization hadn't worked, that Bethe's calculation on the train hadn't matched the experiment, that Schwinger, Tomonaga, and Feynman had each gotten different answers, that the infinities couldn't be tamed. What then? Then we would have the most accurate theory in history, QED, that we couldn't actually use. Every calculation would blow up. Every prediction would be infinite. We'd have a theory that describes reality perfectly in words, but produces nonsense in numbers. Physics would have hit a wall, not a temporary wall, not a "we'll figure it out eventually" wall, a permanent wall, a fundamental limit to what mathematics can say about the physical world. And here's the part that should humble you. We don't know that this wall isn't there. We've just found a way to peek over it. Renormalization lets us get answers without understanding the deep reality underneath. Feynman was honest about this, brutally honest. He said, "I think I can safely say that nobody understands quantum mechanics." He wasn't being cute. He wasn't being humble for the cameras. He meant it. The man who invented the renormalization technique, who drew the diagrams, who won the Nobel Prize, was telling you, straight to your face, "I don't know why this works, and that's not a failure. That's not ignorance. That is the most honest thing a scientist can say. Because the universe is not obligated to make sense to us. It's not designed for human understanding. It's not a puzzle with a clean solution waiting to be found. Maybe, just maybe, reality is stranger than any story we can tell about it. And the best we can do is build better tricks, better approximations, better peeks over the wall, and hope that the next peek reveals something we never expected." So where do we stand? We started this journey with a simple question. How can a single electron, this tiny, almost weightless speck, have an infinite mass according to our own equations? And the answer turned out to be one of the strangest stories in all of science. We saw how classical physics hit a wall, how the electric field at zero distance blows up to infinity, how giving the electron a size doesn't work because nothing can hold it together. A perfect deadlock. We saw how quantum mechanics made it worse, how the electron creates a cloud of ghost particles around itself, virtual photons popping in and out of existence, and how that cloud adds infinite energy to an already infinite problem. We traveled to Shelter Island, June 1947. 24 physicists in a small room, and we watched 3 of them, Schwinger, Tomonaga, and Feynman, independently discover the same impossible solution. Renormalization, a mathematical crime. Negative infinity plus positive infinity equals a tiny, finite number, a shell game, a cheat. And that cheat gave us predictions accurate to 12 decimal places, like measuring the distance from the Earth to the Moon and getting it right to within the width of a single atom. The answer is perfect. The method is insane. And here's what I want you to take away from this. Right now, as you're watching this, there are trillions of electrons in your body, in your hands, in your eyes, in the neurons firing inside your brain as you process these words. Every single one of those electrons is a cancelled infinity. Every atom in your body exists because three physicists figured out how to subtract nonsense from nonsense and get reality. Every molecule, every cell, every thought you've ever had. You are the universe's answer to its own impossible equation. And Feynman? The man who drew pictures on napkins and called his own Nobel Prize-winning work Dippy. He never stopped being honest about what he didn't know. He never pretended the trick was beautiful. He never claimed to understand why it worked. He just kept asking questions. And that, more than the diagrams, more than the Nobel Prize, more than the 12 decimal places, is what makes him the greatest physicist of his generation. Not the answers he found, the questions he refused to stop asking. If this video made you see infinity differently, if it made you feel the weight of a question that has no clean answer, hit subscribe. Because this channel is about those questions, the ones that keep physicists awake at night, the ones that don't have neat endings. Hit like if Feynman's honesty resonated with you. Drop a comment and tell me, do you think renormalization is a genuine insight into nature or the greatest cheat in the history of science? I read every comment, and if you want to go deeper, if you want to see how Feynman's diagrams actually work, step by step, that video is right here. I'll see you there.